João, and is going to present ceramic additive manufacturing functional structures.
Good morning, everyone. Everyone can hear me? Yes? Okay. So now I will present some of the work that I've been doing by the last 3 years. And I will start with some of the works that we did previously since 2016. These are some of the works that we did at the lab. This is the wave wall. Basically, it's a wall that studied the maximum degree of curvature that we can do with ceramic. And actually, it has as well an interior infill interior structure that tried to avoid the passage of heat from one side to another one. Then we do ExaShade that was exhibited at Material Experience in 2018. It's a shading device, basically. Then this is a project of another student. It's a biomorphic column system. Here, wall, another wall like David showed. And here it's myriad wall. It could be a wall or a kind of a radiator because it's a tubular component, so we can pass fluids through it. So, but all of those prototypes, in my opinion, of course, have some problems, and none of them actually truly work. So the wave wall never has a way or a method to hold the blocks together. The ExaShade doesn't support itself, so it needs an acrylic base to support it. Ficus have too much deformations on the base and on the top end. Wall, the interlocking system doesn't work, and the myriad, the piece that should connect the different components didn't work and cannot hold the two components together, so they don't work. And we reached this question, which is how to make ceramic AM a viable and effective method for the production of architectural components, of functional components. And to answer that, we got these 3 key elements. Sorry for that column; it's not that beautiful, but okay. So we work mainly on the first 2. The third one we didn't do anything yet. And to start with this, we start with the columns, with the preliminary tests, which basically this initial test represents an upscale of the size of the components that we produce. So we usually make small size components, and now in this test we are trying to build something a bit bigger. So we designed 5 types of components for columns. Type A, it's structural reinforcement for concrete columns. Type B, it's for thermal insulation. Type C, it's for the passage of infrastructures. Type D, it's for ventilation. And type E, it's a compound component. It tests a different aggregation and discretization method. So type A, it's this simple 3-wall component, basically with 2 walls on the 2 outer walls and 1 interior wall that stacks, that goes on to make the connection to the other ones. And this work can work as a last form work for the construction of concrete pillars. This one is for thermal insulation. We add that wavy surface connecting the interior and the exterior surfaces working as a heat sink, and in addition we can fill that with polyurethane foam. this is for the infrastructures, so we can pass different infrastructures on those holes. And this is for ventilation, which basically have some holes in the interior surface, and those two external heat sinks that absorb and release the unwanted gains. And this is the final type of it, which studies a different discretization method with three components on each level, and wood pieces connecting those. As you can see, I don't have the mouse here. Okay. Those red pieces on the C image right there are made out of wood to connect all the components. So after that, we start to think in materials to be in the middle of the ceramic pieces, because we cannot have two ceramic pieces touching each other because it may crack. So we start to study which material could work better with ceramics. For that, we used a small scale model of the first component that I showed. Here it's a representation of how can we print the internal wall with that support. The support is made with the same material as the other component, and when it dries, that part, the red part, detaches from the main component, and we have that interlocking system there. So basically, to do those tests, to test which material can work better with the ceramic, we do these three this division with three types. So basically, the first one is only ceramic with just one piece, with two stacked pieces and three stacked pieces, only with ceramic. Then we pass to ceramic and the other materials, which has two ceramic pieces and one of separation material, and three ceramic pieces and two plates of separation material. The materials tested was wood, rubber, mortar, glue, and concrete. And then to compare with concrete specimens, we do some concrete specimens with the same dimensions of the ceramic ones. This is how the system works, basically. These are all the specimens that we test. And here it's the compression tests of one single ceramic piece. Here the remains of the tests, and here the values that we obtain. From here, what we can understand is that the material that work better with the ceramic is the wood, but would have a problem. If we are working with natural wood, we need to have in mind that wood, it's not regular, so it has some nodes somewhere. So it has this standard deviation right here. It's the 37% right there. It's quite high, so we can have really high values or really low values. But if we work with natural wood, so we have to have that in consideration. So after that, we go to shell and internal structure tests, which are these ones to build the columns and the beams. We have these three types of shell, I guess. The one that obtained the best results was the third one, and the third one is the one that has less mass. So it's quite strange. It's not strange because it has straight walls, so it can handle better the compression efforts. We test them in both directions. And then we pass to the prototypes, the real one, the big ones. So this is the use of the first type of column that I show in the beginning. So basically, we are using the ceramic pieces as lost formwork for the concrete column and reinforcement as well. And then based on this last design, we start doing the beams. So we start by using a regular hollow brick and steel rods. Then we put MDF plate separating them. Then we have more bricks. Then we apply tension with the torque wrench until it breaks to see if it works or not. Here in detail. And then we do it because it worked. We do it with more bricks, 9 bricks. It's a 2.7 meter beam. We put some weights on top of it and it worked, didn't break. So that we did the connection or a type of connection between beams and columns. Basically, it's that middle component. Okay, we have this component right here that goes inside the column and receives the beams. Basically connecting everything. Everything is connected on that piece, and the column and the beams are tensioned with steel cables that connects to that connection node. This is the prototype. Okay, side view of it. And then we build the beam that should be connected to this connection. Basically, we for the beam we have a wood core and a steel cable working on the tensile, and on top of it we put the ceramic components and the concrete infill. Here the concrete serves to reinforce the entire structure and to connect everything, as we going to see soon. This is how we initially glue the pieces, the ceramic pieces to the wood. And here, filling the gaps for the concrete to not drain out of the pieces. Now the assembly. Okay. After that, we put some steel anchor points. Basically, these are screws that are connected to the wood. And then we fill everything with concrete. We put this steel cable inside. It's an 8mm steel cable. And here it's the main result. We put some weight on top of it. It's not too much weight. It works. And now these are some renderings that we did, some building concepts that we can showing what we can achieve with this. That's a simple one, and it is a building with 2 stories. Well, and that's it. Thank you.
Thank you, João. So, open questions. That's round we each carry the questions for
Okay.
Billy and better.
Yeah, thank you, João. Very nice presentation. A lot of prospect. The details are really very well started. So we're going to push it to the whole approach to another level. I have one question, one consideration. The question is, if I understood correctly, within your ceramic components, you kind of have an infill, and therefore the concrete that you pour inside, that's inside, will not be continuous. Why would you choose to do that? Why wouldn't you just have lots of just the outstream that?
Okay, the question was about the competence beam, right? Why I have that infill, ceramic infill? Yeah, and the concrete, it's not continuous. Well, we put initially it was intended to be continuous, but when we tried to print and fire the ceramic pieces, they bend. So I have to put something inside that, and that structure will allow the concrete to fill everything. It's not entirely connected, but it's connected sometimes. What? Which one?
Yeah,
this is.
It's larger components where the surrounding composites are already part of the slab.
Sorry.
So, yeah.
Oh.
Right now, but would they be like larger elements part of the slab?
Yeah. Yeah, that's an input that Professor Polkers already gave me. Yeah. Actually. Thank you.
Pretty much in the beginning, you show the slides with the whole project. So, can you give it back?
Yeah. Mm. Okay.
So if you do some self-criticism by saying, okay, this doesn't work, for example, extra shade doesn't for itself, only the structure of the myriad is not so one type. But what I don't get about this, you use any water, because if you have some layer of water, this should work out. And speaking for the regulator, like here, and you do the water type and water, so thank you. That's just don't get it one. Step one. So maybe it's more question for videos because that's not all of it.
We're absolutely right. Yesterday, someone already discussed this problem. When we really nice when weeks, and then how to put them together. If with a mortar in a classic way, or with a 3D printing heating system, etc. So João abandoned the idea of studying how to make this feasible, how to put together bricks. For sure, you need the idea of that showed yesterday an image of a small project we have in the context of the energy Portugal projects, where we combine those tubular ceramic elements with also polymeric or even metallic 3D printing joints. So we can perfectly together those ceramic with specific polymeric or metallic joints. So I also agree that some of those criticisms are quite pessimistic.
Yes. Well, the first one it doesn't, because
Yeah, he wants to himself all helping his arguments for what he wants to do, I guess.
obviously.
So we're just discussing here the failure of these five previous experiments, but yeah, we're saying it's overcriticism from João himself. Something could be improved here with some
If I
connectivity.
told that I could not put the question in the next slide, so.
Yeah.
And these 2 centimeters accommodate any.
Yeah, but you're doing that and it's perfectly well, fine, so it's, yeah. Sorry, just one more question from Philip.
Slide what? Six. Okay, this one.
26.
26. Okay. 6.
Do I read this correctly, that ceramic one has like an incredibly much higher strength than anything else in this table?
Yeah.
And then only if you combine. So with row one, is that part of the connection of ceramic one? And
No, ceramic one, it's just one piece of ceramic, so without anything. Ceramic two, it's 2 pieces of ceramic, so yeah.
And for sure, it's not local, it's unit is megapascal speed.
So yeah, Philip was asking about first result on first sample ceramic wine compared to the others. Why is such a huge difference? So it's the main point.
The critical compressor loading draws so much of just the way it leaves that.
Yeah, it's exponential.
Even in concrete, you've got a leader, you can start work and
Yeah, but the main problem is that the ceramic pieces are not completely flat. So when we stack 2 or 3, they crack.
Lot better using. Still on that same, complementing what you guys asked. It's just that there's how many samples to test up to that sample variation. Like
Just 3.
just
3. On this, yeah.
and you could isolate, of course, definitely will increase the number of samples there.
Thank you.